So the presentation is that I would like to give a talk today is about characterization and optimization of blue-enhanced optical honeycomb detector sensors, basically. And this work is in collaboration with University of New Mexico and RPI, Shima, Nezhadbadeh, Ghasemi, Alexander Graham, and Alexander Neumann, and Steve Brueck and myself are from University of New Mexico, and Asif, Chowdhury, Bassem, Fahs, and Mona are from RPI. So here's the outline of my presentation. I'm going to start with a very quick overview of honeycomb optical sensors. Then I'm going to discuss about the modeling and optimization of honeycomb responsivity, and then I'll discuss about the test chip that we designed and characterized using AMS technology, and then some experimental results and conclusions. So in this slide, you can see the responsivity of commercially available photodetectors. And basically, you can see in this slide that normally the responsivity at the blue region, when the wavelength is around 400 nanometers, is normally very poor. And basically, again, if you can enhance it, as you can see in this slide, the price, of course, is going to be much higher than the basically nominal detectors. So the main reason for having a poor responsivity in the blue region are basically two reasons. One is the blue photons have high energy, and basically the efficiency is not that good in order to convert the high energy photon into just one electron hole pair for every photon. And the other reason is blue photons heavily absorbed at the surface, and that's because of the high absorption coefficients of blue photons. Basically, the key point in this case, in order to increase the quantum efficiency, would be to bringing the depletion region up to the surface to be able to basically enhance the responsivity of the detector in that region, in the blue region of operation. So in this slide, you can see actually the PN junction. This is a standard way of making a photodetectors. And of course, the simplest solution in order to bring the depletion region up to the surface would be reducing the junction depth, which has some practical limitations. You cannot go below certain range. However, when you look at this basically PN junction, you can see the edge of the detectors automatically brings up the depletion region close to the surface. And that's exactly an elegant way to basically have a very close to surface depletion region, and that's exactly the way that we are using in our technique. So when the blue photons basically hit the N+ region in this case, once it creates an electron hole pair, because again it's going to be absorbed exactly on the surface of the silicon, it doesn't get the opportunity to get into the depletion region and get basically separated to create an electron hole pair. However, in the next example, if you can see this blue photon hits the surface, it's going to create an electron hole pair in the depletion region where they can be separated and contribute into photocurrent. We actually experimentally measured this and observed this behavior by basically doing the laser scan. As you can see here, the laser beam scan was on the detector, and as we move the laser around the edge, once we get to the edge, you can see the peak over there, and that confirms exactly the point that at the peak of basically at the edge of the detector, the sensitivity to basically the blue photons are high, and mainly because of the depletion region that gets into the surface. So in order to basically get the best benefit of this basic structure, of course, the best approach would have been having a honeycomb structure, which we propose in this work. So in this case, you can see two separate detectors. One is the conventional photodetectors when the entire region is N+ region, having a PN junction. And in this case, as you can see, the depletion region is actually buried underneath of the N+ region. So on top, basically, you see the N+ region. And on the other hand, on this honeycomb structure, what we have is that due to the opening here, you can see the yellow depletion region actually comes to the surface, and that's exactly where we have the highest responsivity for the blue photons. Of course, again, in this case, the gray region, which is our N+ region, is going to have the conventional responsivity. However, the the yellow region, when the depletion region is on the surface, they have the highest responsivity for the blue photons. On the other hand, as you can see here, the price that we have to pay, of course, is the white region, where we have the P+ region in that case, and there is no basically photosensitivity within that range. Therefore, it's important to optimize this design and optimize the specificity, the size of opening, and make sure that we get the best benefit of this honeycomb structure. For example, if, for example, the honeycomb in this honeycomb structure, the let's say opening is 0, it's not open basically, or small. If the opening is small, we cannot get the full benefit of the depletion region that comes to the surface, and therefore we don't get the best benefit of the honeycomb structure. And if it is too large, in fact, because of the larger white area, we actually lose responsivity in that range as well. So it is important to find exactly optimum size for the opening in order to get the best result. So in order to optimize the process, of course, we need a model in order to find exactly how much responsivity is as a function of the dimensions of the device. So in this case, we're going to have some definitions here. For example, D is the width of the N plus region. We assume X and X0 is basically the width of the opening, and then we have width of the depletion region and the unit cell size. We assume that the responsivity in the gray region, which is the N plus region in this case, is RA, and then responsivity in the depletion region is RE. A is for the area, E is for the edge. The equation in this case, if we find the effective responsivity for the honeycomb detector, is the weighted sum of RA and RE, depending on how much area they have with respect to normalized to the unit cell area. And that's exactly the equation we get. Of course, this is true only if basically depletion, the opening area is not fully depleted. If the opening area becomes fully depleted, then in fact the equation for responsivity is going to be limited to the opening area, basically normalized to the unit cell area. So these are the equations that we get, for optimization. And in order to basically design an optimum photodetector, we are going to have basically we need to find these two parameters. One is D, and the other one is X naught, which is the opening size and the width of the depletion region. In this case, we are going to use the top equation, which is the equation where the opening area is not fully depleted, and then find the basically maximum within that range. I'll show you later exactly why that region actually gives us the maximum responsivity. So here's the equation we have, and in fact, if we just plug in the value for XU, which is the unit cell size, we are going to get the basically XU is X naught plus D. If I plug in value and simplify the equation for responsivity, here's the equation that I get for responsivity as a function of basically X naught and D. Based on this equation, you can see that D appears only in denominator here. That basically proves that in order to maximize the responsivity, D has to be minimized. And therefore, that's very simple optimization process. D has to be minimized. That means that the width of the N plus region has to be as small as possible, which basically is defined by the design rule and the lithography process that we are using. Once I basically plug in D value or as a D min here, then my responsivity is going to be as a function of X naught. I can take a derivative with respect to X naught and find the peak value or the value for X naught for the opening that then maximizes the responsivity. So these two equations give me exactly the amount that I need for optimal design of the honeycomb detector, which basically is the D is the width of the depletion region, X naught is the basically opening size. So in this graph, you can see how this calculation can be done and optimization can be done. Here it shows the responsivity of the honeycomb as a function of the opening size. And then you can see that as D changes, basically the peak responsivity changes. And the peak responsivity is, in fact, when D is the minimum, which in this example is the 0.35 micron process, which gives us the basically maximum responsivity in that case. And if, again, another example is that if X naught in this case goes to 0, that means that it becomes a solid detector without any opening. The responsivity has to be equal to the responsivity of the solid detector, which is 0.011 in our example. And if again, X naught, the opening become extremely wide, that basically degrades the responsivity, and that is not desirable. Of course, the optimum desirable value in this case is about 1.1 micron. That gives us the basically peak value for the responsivity when the D is 0.35. So that's exactly gives us an idea exactly how much the opening of the photodetector has to be for the honeycomb structure, and basically and also the width of the device. So on the other hand, again, if you look at it here in this case, is that when X naught is below 0.9 approximately, which is 2 times W, in fact, it becomes fully depleted. So we can see that again in this example, the peak value goes beyond the fully depletion basically case. One important observation we had is that when the device goes to fully depleted region, in fact, the responsivity becomes worse than what we anticipated with the simple equation. And the reason for that, we observed that it is mainly because of the dead space. And just to discuss a little bit exactly what dead space means is that, again, if it is fully depleted, as you can see it here in this range, the opening area, the electron hole pair that is generated in the middle is going to be basically absorbed by all four corners, and therefore, in fact, the effective electric field in the middle is zero. That means that, in fact, there's a dead space in the middle of the basically spacing, and that is basically reducing the responsivity. So in order to characterize the photodetector and the technology for this photodetector, what we did here is that we designed three basically samples for the detectors. One is a solid and two honeycomb detectors with a pitch of 1.2 micron and 2.4 micron. We needed three designed because we have three parameters to extract. One is RA, RE, and W. And again, we did some measurements using the spectrometer that we had in our lab, and then we measured the responsivity as a function of wavelength for two cases. One is for the edge, and the other one is for the area. As you can see here, the edge responsivity is always higher than the area responsivity, and that's exactly what we anticipated, mainly because the depletion region is close to the surface within that range. Also, if you notice here, in fact, the impact is much more. So again, you can see that this is almost a factor of two, basically enhancement in responsivity at the edge. That's exactly what we also anticipated in that. So, and also the width of depletion region was basically measured at 0.47 micron in this case. In order to see exactly the response, I have here the responsivity of edge over responsivity of area, the ratio, and you can see again, around 400 nanometer, we have a factor of about 2 in responsivity between the edge and the area in that case. Based on the parameters that we have here, which is RA of this 0.01, RE of 0.02 with the depletion region of 0.47, we can optimize the size of the photodetector based on the technique that I mentioned earlier. We come up with the opening of 1.1 micron, and the width of basically N plus region becomes 0.35 micron because, again, it's limited for 0.35 micron process, AMS fabrication process. And again, in this optimized process, we can actually find the quantum efficiency for the solid and basically optimal honeycomb detector. And again, as you can see, for all the wavelength, optimal honeycomb detector has higher responsivity. And again, if I do find the percentage of improvement, I can see at 400 nanometer range, the percentage of improvement is about 40 to 60 basically percent, depending on, of course, the wavelength that you have within that range. In summary, basically, I presented a novel honeycomb photodetector to enhance the blue responsivity. And also, I developed an analytical model for honeycomb responsivity, obtain an optimal honeycomb design for maximum responsivity, and also we design a fabricated an AMS process in order to do the characterization for honeycomb detector, and I presented some results. At the end, I would like to acknowledge the support from National Science Foundation under LISA, Lighting Enabled Systems Applications Center, as well as the contribution from AMS. Thank you for your attention.